Today in our notes, we're looking at a topic called simplifying radicals. Just like simplifying fractions or expressions, this is writing a radical, which is like a square root, as a different, simpler version of itself, but we're not changing the number. So, for example, if I had the square root of 32, that's a fine number. It's somewhere between 5 and 6 because it's between 25 and 36. But it's not acceptable as a final answer in the same way that 8/6 is not acceptable as a final answer. We have to simplify this, divide both top and bottom by 2, and make it 4/3. Here, we need to break up this number inside, and if there's anything that can be square rooted evenly, like a perfect square, then we want to take that out. So this ends up being 4 times the square root of 2. And as we go through the notes, we'll talk about how we get to that and how you can do it. But that's the idea, is we're simplifying these so that they're in an acceptable final format as far as like the rules of math are concerned. But we're not changing numbers, just like any time we do simplifying, we're just rewriting. So a radical expression has 3 important parts. Let's label those. We have the index, the radical, and the radicand. R-A-I-D-I-C-A, just like radical, but then it ends in N-D instead. So this symbol, this like check mark with a tail on it that you've used for square roots, has a name. It's called a radical. And when we don't have a number here, like when we write square root of 32, like I just did, there's no number here. It's just a radical and a radicand. So it's understood or assumed that there's always a 2 here when it's blank. Kind of like when we have x, we know that's x to the first. Or when we have 4, we know that's 4 out of 1. So these hidden things, or that's a 1x to the first, in fact. So there's a hidden 1 there, there's a hidden 1 there, there's a hidden 2 here. That's just, we assume it's a square root because that's the most common type of root that we use. So if the index isn't stated, it's implied to be 2, and we call that a square root, which you're already familiar with. So we can put a different number for that index. So just to be clear, square root of 32 means if we have a number, that times itself would be 32. So that's why it's a square root, is we need to square something to make 32. But if I wrote the 4th root of 32, that would mean I need something that multiplied 4 times in repetition would equal 32. So that index is basically what level of root are you taking? Is it a square root, cube root, or something bigger? Properties of radicals, we can basically cancel out a square and square root. You probably already know that. So if I have the square root of 4 squared, that's going to basically cancel and get rid of the square and the square root, but that works with any level of index. So if I had the 5th root of 2 to the 5th, that would also cancel out. And the reason for that is radicals and roots are just fractional exponents. So there's one law of exponents we didn't really talk about, which is x to the m over n is the nth root of x to the m power. So this one where I have the 5th root of 2 to the 5th, that's like saying 2 to the 5/5. And as we know, 5/5 is 1, so that's just 2, right? 2 to the 1st power. So we have an example, that was this one. So the square root of 4 squared, you can put that here as your example. We also have properties about this middle one is super essential for what we're going to be doing here. The idea that we can break up a number that's under a radical and put it under separate radicals. So we'll do the square root of 4 times 9 as an example. And we want to see that that equals the square root of 4 times the square root of 9. So we can basically separate out those things. And we should know that's true from our laws of exponents, because basically what we're saying is this is 4 times 9 to the 1/2 power. And we know that that 1/2 would get distributed to each of the multiplied things in the parentheses. So let's just evaluate this and see. So this one is the square root of 36, and we know that that is 6. This one, the square root of 4 is 2, and the square root of 9 is 3. So we know that 2 times 3 is 6. So hopefully that helps you see that this is okay, that we can take a number and kind of break it apart into separate pieces like that. So that would be an example to go here as number 2. And then finally for number 3, we could do something like the square root of 16 over 4 equals the square root of 16 over the square root of 4. So we'll do a similar thing like we just did with multiplying. 16 over 4, so this would be the square root of 4. We simplify 16 over 4, and the square root of 4 is 2. If we simplify them separately, the square root of 16 is 4, and the square root of 4 is 2, and 4/2 is 2. So we can see that whether we write the radical separately like this or all over one thing like that, it's the same. Very similar to if we had like 2x plus y all over 3. That means the exact same thing. It's equivalent to 2x over 3 plus y over 3. So the radical, or the root of this whole fraction, is the same as the root of the numerator over the root of the denominator. So that's our example for number 3. Now let's talk about what simplifying radicals is about. It requires us to understand something called factoring. Factoring is where we break a number apart, very similar to what we did over here with this 4 and 9. It's like going backwards. So we turned 4 and 9 into 36. What we're going to do is turn 36 into 4 and 9, or something like that. So there's 2 different ways, at least, there's probably more, to visualize this. I'll show you both of them as examples, and you can do the one that you like the best. So we start off by breaking this number into 2 separate factors. So 2 things that multiply to make that, and it does not matter what those 2 numbers are. So for example, I'm going to pick 10 because it ends in 0, and 18 because 10 times 18 is 180. Now we look at our factors, and unless they are prime numbers, because this method we're doing is called prime factorization, we're going to break them down further. And we're going to make this 2 times 5, and we're going to make this 2 times 9, or 6 times 3, or whatever. 2 is prime, and 2 and 5 are prime, but 9 isn't. It needs to be broken down further into a pair of 3s. Now that we're at the bottom of all these branches, we have, I'm going to highlight here, we have these numbers as our ends of the branches. We don't care about anything along the way, because these 2 3s I highlighted are the same as the 9 above them. So once we have these, what we've discovered, or what we've said, is we can think of this 180 instead as being 2 times 2 times 3 times 3 times 5. The reason that's useful is the property we looked at over here in number 2. So I'm going to erase this tree because we've seen it and we need space. So now that we know this is square root of 2 times 2 times 3 times 3 times 5, I could write that a little differently. I could think of that as square root of 4 times 9 times 5. And we know that the square root of 4 is just 2. It's not actually a radical at all because it's a perfect square. And the square root of 9 is 3. But the square root of 5, we can't do anything with that. It can't be any more simple than that. And we know that because it's a prime number, so there's no way to find a perfect square inside of it. And then finally, 2 times 3, we can combine that into 6. So our final answer for square root of 180 is 6 root 5. So that's the process, and what it comes down to is we're breaking down all these prime factors, and we're looking for pairs of factors. So notice these 2 2s became a 2, and these 2 3s became a 3, because we're square rooting it, so we need 2 of them to make a regular number. As a quick aside, If we were doing like a cube root or something bigger, we would need a larger set of numbers. So let me erase some stuff over here real quick. And we won't go much into this because it's beyond Algebra 1, but you know we like to challenge you guys with things that are a little above level. So let's do square root of 360, but not square root. We're going to do cube root. You do cube roots the same way. You do this factoring and you split things up. But instead of we're looking for 2 of a number to make a perfect square, now we need a set of 3 of the same number to make a perfect cube. So we have 2 times 2 times 2. So our cube root is going to turn those into a regular 2. That's our first property. We're doing the cube root of a cube, and we get a regular 2. But we don't have enough 5s or 3s to make a perfect cube, so they would all stay inside of our radical. 3, 3, 5. This is a cube. And then we would just combine them back into the bigger number now that we know they can't be any simpler than that. So we would do 2 times the cube root of 9 times 5, 45. Like that. That's pretty much it. So we won't address higher order radicals beyond like just an aside. It won't be something you're tested on this year. It will be something you need to know later in math. Let's do these other examples. I'm going to do this one slightly differently. So the method I did on the first one, like what we did over here on the square root of 360, is called a factor tree. So we branch it out, and what we're looking for is the ends of all those branches. This method, I think, is called a birthday cake method. It's new to me. I've never done it before, but let's try it out. So we can start with 54, and we're going to start from the bottom and build up instead of the top and build down. We make a little hat over this, kind of like a division symbol, and we take out the smallest prime number we can. So in this case, the smallest prime, since this is even, will be 2. Then we divide it and put 27 up here, and then stack it to the next level. Next, we're going to pull out the smallest prime number we can. This is odd, so 2 doesn't divide into it, but 3 does. When we divide by 3, we get 9. Then we're going to pull out the smallest prime, which is 3, and we're left with 3, which is prime. So with the tree, our prime factors were the ends of the branches. With the birthday cake stacking method, our prime factors are all of these divisors and then the final quotient, which is a prime number. But the process, the idea is the same. We're trying to find pairs of factors because 3 times 3 is a perfect square. So when we square root that, we're going to get a regular 3. And remember, all we're really doing there is square root of 9, right? And we know square root of 9 is 3. So that pair of 3's becomes a regular 3 outside the radical. We get to pull that out of there. The other 3 and 2 don't have a partners, so they get stuck inside the radical, and they stay as square root of 6. Square root of 6 cannot be simplified any further because it doesn't have any perfect squares inside of it. Let's do one more of each method. So this one, we have 10, 15, 2, 5, and 3, 5. So my 4 prime factors are 2, 5, 3, 5. I look for pairs. I have a pair of 5s. So this 5 and this 5 are able to pair up and escape from the radical. The 2 and 3 can't escape, just like in problem 2, so they stay in here as a 6. But there's a really important difference between problems 3 and 2, and that is we had 3 square roots of 150. So there's already a 3 on the outside that was multiplied by what we have. So when we take out this 5, it has to get multiplied together. So we multiply these, just like on number 1, we multiplied the 2 and 3 and turned them into a 6. So our final answer here is 15 root 6. And losing this number, the coefficient that was already outside the radical, is one of the most common mistakes in this section. So watch out for that. Be careful. Let's try the birthday cake one on this. So I'm actually going to start with the -4 to make sure we don't lose it. So I'm going to put -4, and then I'm going to put my 320 in here. We're going to take out our smallest prime, which is 2, and then we're going to have 160. We're going to take out our smallest prime, which is 2, and we're going to have 80. 2 again leaves us 40. 2 again leaves us 20. 2 leaves us 10. And 2 leaves us our final prime, which is 5. So the thing I like here is this negative 4 is already here. The problem is I've listed it along with all of these things that are in the radical. So I don't know if that's the best way of writing it, but we're looking for pairs. So I have a pair of 2's, I have a second pair of 2's, and a third pair of 2's, and then a leftover 5. So I end up with negative 4 times 2, that was the first pair, times 2, that's the second pair, times 2, that's the third pair, and my 5 that's all alone has to stay inside of the radical. Now I want to crunch together all these outside numbers and multiply them into a single number. So 2 times 2 times 2 is 8 times negative 4. So our final answer here would be negative 32 root 5. And yeah, that's that. So let's look at the other way of doing this. So this is the more old school way. It's a little more mental math and a little less, I guess, simple. When we do prime factorization, there's no way to get it wrong. No matter what pair of factors you start with, you're going to end up with the same list of prime factors. But when we do the perfect squares method, we're looking for, instead of dividing all the way down to the bottom level, we're looking to just divide it into the biggest perfect square, or really any perfect squares. So notice on number 1 with method 1, we found 2 2's, and then we put them back together into a 4. We found 2 3's and put them back into a 9. So in this method instead, we're looking for perfect squares that divide into our number. So that's a little harder because we're not dividing by 2 or 3 or 4, or 2 or 3 or 5. We're dividing by squares like 4, 9, 16, 25, bigger numbers like that. So here I can pretty easily see that 9 divides into this. So I know that this is square root of 9 times 20. And then I would say, what perfect square is part of 20? So I have 9 times 4 times 5. So instead of going bottom up, we're going top down and trying to do fewer steps, but it's harder mental math. At that point, we can square root the 9 and the 4 to bring them out, and we get 3 times 2, and then root 5. So our final answer, just like it was in method 1, is 6 root 5. So they work the same way, and you can actually do like a hybrid of them. Notice this is called the largest perfect square. So technically, I was intended to break this one down into 36 times 5. But maybe I didn't see that 36 was the biggest perfect square. If I find any perfect squares, like the 9 and the 4, that's already getting me a lot closer to my answer. With number 2, it looks like our perfect square that comes out of there is 9, and we're left with times 6. 6 doesn't have any perfect squares in it because it doesn't have a 4 in it, and it's smaller than 9. So that means we just have 3, which is the square root of 9, times the square root of 6. This one definitely has a 25 in it because it ends in 50. So I could divide this into 25 and 6. So again, 6 has no perfect squares in it. So and remember, this is in here, and the 3 is out here. So I'm going to pull out a 5 as the square root of 25, and I get 15 times the square root of 6. So one other error that's common I want to mention is when we bring out this 5 and there's already a 3 there, sometimes students will add this instead of multiplying it. But remember, there's no addition symbols. This is all one single term that's multiplied together. So this is 3 times root 150. There's an invisible multiplication here. So when we take that 5 outside, the times is still there. We're still multiplying those numbers, and we get 15, not 8. And then this last one, 320. I mean, I know there's a 4 in there. So since I can't immediately see the bigger perfect square, I would just start with 4. And then I end up with 80. Well, 80 has 16 in it because it's 16 times 5. So I can do 16 and 5. But let's say I didn't see the 16. I could have done 4 and 20, and then 4 and 5. So there's kind of an in-between between prime factorization and largest perfect squares, where you just find some perfect squares that are in the number. So now I have negative 4, so we don't want to forget the negative 4, times the square root of 4 times 16 times 5, and then I'll just square root my perfect squares. I get a 2, and I get a 4 out. So negative 4 times 2 is negative 8, times 4 is negative 32, square root of 5. And you can see that either of these methods, or I'm not really doing largest perfect square correctly because I didn't find the biggest one, but it doesn't matter. As long as you break it into pieces that have perfect squares, whether you go to the primes and find the pairs of them, or whether you just find perfect squares, either way is going to get you to the exact same answer. We got all the same answers both ways of doing this. So you can kind of pick and choose or do something in between. It doesn't really matter as long as you understand the heart of this is find perfect squares and take them out by square rooting those pieces of what's underneath the radical.